let's look at orthogonality once more, orthogonality of vectors to begin with, and what that says about projections. If you were to visualize vectors as line segments with arrows, orthogonal vectors are really perpendicular vectors. Vectors that are perpendicular to each other are orthogonal to each other. So orthogonal is just a fancier word for perpendicular. But what does that mean though? It means that the inner product, the dot product, is 0. It also means that the projection of one of these two vectors onto the other vector is going to be 0. So orthogonal is kind of like the opposite of a scaled version. So scaling is like collinear in our case, or parallel. Orthogonal, being perpendicular, is the complement of that. So let's look at the size of the vector once more. We defined the size, the norm of the vector, using the symbol, the double bar here. That is the square root of the sum of the squares of the components of the vector. And that, as you know, is the square root of the dot product of the vector with itself. If you scale the vector by a scaling factor s, then the norm gets scaled by s, but the absolute value, because the norm is always positive. Although we used it multiple times so far, let's state this once more. Two vectors a and b are orthogonal if and only if their dot product is 0. A dot b, which is a transpose b or b transpose a, has to be 0. So it goes both ways. If a transpose b is 0, then the vectors are orthogonal, and if they're orthogonal, then a transpose b is 0. The proof is kind of interesting, so let's take a look at the proof a little bit. A transpose b, as you know, is the accumulated product, component by component, element by element, between a and b, is a sum product. And that's a scalar, it's just a number. And if you think of it as a 1 by 1 matrix, a scalar is a 1 by 1 matrix, its transpose is itself, because it's just one number. What we can say is that A transpose B is the same as its transpose, so that is the same as B transpose A, which is how we can write that. So that is one statement. Then if A is orthogonal to B, then AB and A plus B in red, blue and green respectively will form a right angle triangle. This is the origin here. Our vectors all start from the origin, but you can just move it to that tip of the red vector, move the blue vector to the tip of the red vector to see the right angle triangle. And from Pythagoras' theorem, you know that the square of the hypotenuse is the sum of the squares of the other two. What's the hypotenuse? Is the green guy. So the norm of a square plus the norm of b square is the same as the norm of a plus b, the whole thing squared. We know the norm of a square, that is a transpose a, b square is b transpose b. Then the norm of a plus b, the whole thing square, is the dot product of that vector with itself. So you get that green expression there. You know that the transpose of a sum is the sum of the transposes, so you can write that. Then you can expand it. So you get the left-hand side, that guy right here. The right-hand side, you do the expansion, A transpose A, then A transpose B, then B transpose A, then B transpose B. So you get A transpose A and B transpose A, which will cancel off from the left-hand side and the right-hand side. So you get 0 equal to A transpose B plus B transpose A. Well, we know that those two guys are the same. That means A transpose B is the same as B transpose A, and both of them are 0. Well, we can take an example and take a look at it once more. I have a vector A that is 5 and 1. I call it half, 10 and 2. Then I have half minus 1, 5. So if I move it to the tip of that one and draw the right angle triangle, I'll get A plus B to be half, 9, 7. Now, the size of A, the norm of A, is square root of 26, because this is 5 and 1, so 5 square 25, 1 square 1, so square root of that. And size of B, being half of that in size, is going to be half of square root of 26. A square plus B square becomes 65 by 2, and A plus B, the whole thing square, becomes 65 by 2. It has to. That is the oldest theorem that we have in the book. And then A dot B will become some product of the elements with the scalars outside. So minus 1 times 10 plus 5 times 2, that is a minus 10 plus 10, 0, and then scale by 1/4. So the dot product indeed is 0. Now orthogonal matrices are the ones with orthonormal columns. Orthonormal means orthogonal and normalized, perpendicular and unit length. So one good example, as we saw, was the identity matrix. And the condition we saw was that Q transpose and Q will have to be the inverses of each other. That means Q transpose is equal to Q transpose Q equal to I. And this follows from the fact that the columns are orthogonal and of unit length. Each element in this product is going to be the dot product of the ith row of the first matrix with the jth column of the second matrix, and that is given to be 1 if the numbers, the indices match, and 0 if they don't, and then it just gives you the identity matrix. We saw all that in the last video. Let's take an example of this, a rotation matrix. Rotation matrices are interesting for many reasons. We saw that orthogonal matrices don't change the norm of the vector that it is transforming. What does that mean? It means that all it can do are the following things. It can rotate a vector or reflect a vector, shuffle the rows of the vector, shuffle the elements, so that will not change the norm either. So permutation matrices are orthogonal matrices or rotation matrices. So that's an interesting class of matrices. Let's take a look at one of them. In R2, one angle will completely specify the rotation. So it is Q with the angle theta, so you can write it as a Q sub theta. So inverse of that rotation matrix will have to be something that rotates in the opposite direction, so minus theta. So that is something that we kind of want to verify. In R3, it becomes already very complicated. You need 3 angles. Those of you who play flight simulation kind of games, they know that is it's the pitch going up and down, nose up or nose down, yaw, which is side to side kind of rotation of the plane, and the roll, which is from side to side this way of the plane. So those are the 3 angles, and you need those 3 angles. It's a complicated matrix, 3 by 3 matrix with those 3 angles that will give you the rotation in 3 dimension. But we'll just look at 2 dimension just because these are interesting matrices. So as we know, if you take a vector, a unit vector in R2, so along the x-axis you have Q1, along the y-axis you have Q2, and you can take any vector on the unit circle, and that will have components cos theta along x, which is this guy here. If you complete the right angle triangle, this is adjacent side, so that's cos theta, and the hypotenuse is 1, that's why it's 1 times cos theta. Sin theta will be the vertical direction. So that's the general unit vector in R2. And if you were to take the vector Q1 to Q1 prime, then the same matrix will take Q2 to Q2 prime. Everything is getting rotated by angle theta. So if you do the trigonometry there, that will turn out to be minus sin theta. So this will have a component minus sin theta, and the vertical component, the second component, is going to be cos theta, because theta happens to be the angle between the vertical axis and Q2 prime. So once you know what the unit vectors transform to, you can write down the matrix that does the transformation. So the rotation matrix Q parameterized by theta is cos theta sin theta in the first column and minus sin theta cos theta in the second column. Now you can verify that the determinant is actually 1. Cos squared theta plus sin squared theta is 1. So you can see how something that you learned in trigonometry a long time ago, it's actually completely consistent with something that comes out of linear algebra. It has to be. So rotation matrix, as we wrote down there, is cos theta sin theta minus sin theta cos theta, reading it column wise. Rotation in the opposite direction, when theta becomes minus theta, that has to be the inverse, because you're just undoing what the rotation matrix did. So let's do that. Cosine of minus theta, minus sine of minus theta, and so on. Using some trigonometric identities, you can write it down. That becomes cos theta minus sin theta cos theta here. And look at the original matrix here. They are indeed transposes. You just transposed these 2 elements. So the inverse is indeed the transpose. Beautiful, isn't it? Now you have one more way in which you can do the transpose. Swap the diagonal elements. So cos theta and cos theta, swapping doesn't make any difference. Change the sign of the off diagonal elements. So sine theta and sine theta here, change the signs. So one of them that wasn't negative will become negative, and divide by the determinant. Determinant is just cos squared theta plus sine squared theta, and that is just 1. So you get that also using our analytic way, the inverse, not by arguing that is the rotation in the opposite direction, but it is really indeed the inverse by using our 3-step way of computing the inverses. So rotation matrix is kind of interesting to illustrate the properties of orthonormal matrices, or rather I should say orthogonal matrices with orthonormal columns. Why are the columns orthonormal? What's the norm of this guy? Cos squared theta plus sine squared theta, 1. Same as the second guy. And what's the dot product of those two? Cos theta sine theta with a negative sign, sine theta cos theta with a positive sign, they add up to 0. Perfectly consistent. So that brings us to the end of our discussion on orthogonal matrices. Now, the next step, of course, is to take any matrix. We'll start with a square non-singular matrix and try to find an orthogonal version of that matrix that corresponds to the original matrix, corresponds in some loose sense. And we'll see what that means and why that is important, and that is the Gram-Schmidt process. That will be the topic of the next video.